We will continue doing problems on internal forces, and I will start to do some problems on shear and bending moments diagram. For the following beam, draw the shear and bending moment diagrams. As you can see here, we have a beam supported by a pin and a roller. So at the pin, you know that the reaction is, we have a reaction in X and a reaction in Y. So we have AX and AY. And at D, we have only a roller, so it's DY. Okay, we have only a Y component. Now, before being able to draw the shear and bending moment diagram, the first step is to calculate the reactions. Okay, because the reactions will affect the shear and bending moment diagram. So this is AY, AX, and this is DY. Now, first, we have three equations, three unknowns of equilibrium for AD. No forces along X, so when we write sum of X equals to 0, we get that AX is 0. Now, to get AY, I can do, for example, sum of moments about D. If I do sum of moments about D equals to 0, I can select the positive direction as I want. So, for example, if I consider the clockwise as positive, then I will have that AY times 2 plus 3 plus 2, so AY times 7, AY times 7 minus, I have here a 14 kilonewton force doing a counterclockwise moment, so minus 14 times the distance to point D, which is 5, and also for 28 is a counterclockwise moment, so minus 28 times 2 equals to 0. The only unknown in this equation is AY. I get AY. I get AY equal to 18 kilonewton. Now, once I have AY, to find the DY, the easiest way is to do sum of forces, or also I can do sum of moments about A equals 0. So both will give me same result. So now if I do sum of forces along Y equals to 0, I have AY minus 14 minus 28 plus DY equals to 0. So I get that DY is 24 kilonewton. Once I have my external reaction, I can start to build my shear and bending moment diagram. Now, always for shear and bending moment diagrams, do the diagrams close to each other, and one below the other, because this will help you, as we will see here. Okay. So first, in order to present just the shear diagram, we start from at A. What do we have? At A, we have an upward force, and an upward force will cause a positive jump in shear. This is why we start from, in the graph of V, we start from plus 18, okay? Because in the course material, we have seen that a positive force will cause an upward jump in the shear diagram. So we start by plus 18. Now, from A to B, we don't have anything, no change in load. So V will remain constant, okay? It will remain constant until reaching point B. At point B, we have a downward force of 14 kilonewton. A downward force will cause a downward jump of 14. So we were at a value of 18. We should do a jump down of 14. Then we will have a value of 4. So here it is 18 minus 14 equals to 4. Now, from B to C, no change. We don't have any load. So V will remain constant. Now, at point C, we have a downward force of 28 kilonewton. So we will move downward a value of 28. 4 minus 28 will give us minus 24. Then from C to D, no load, so V remains constant. And to verify our calculation, okay, always here just after D it is 0, okay, and just if I do just a cut after D, I don't have anything. So the value of shear at the end should be equal to the opposite of the reaction. Okay, why? Because after the reaction I should go to 0. Okay, and here it's an upward force, so the reaction will do a jump of plus 24, and plus 24 will get me back to 0. So it's right that I should end here by minus 24. Okay, any question on shear diagram?
Doctor, question. If we
Yeah.
had a vertical force, sorry, a horizontal force, usually كيف بنرسمها على الشير؟
A horizontal force will not affect the shear diagram, it will affect the normal force diagram. يعني here you don't have any x force, so at any cut you do, what will be the normal force? If you do a cut, okay, the normal force is everywhere 0. In case you have a x, for example, let's say you have a load here, a force here of 20 Newton, for example, then Ax will be equal to 20. These forces will not affect the shear diagram, but they will affect the normal force diagram. So if you draw the normal force diagram n, the variation of n, at any section here, what will be the value of n? So this is n function of x. If you do a cut, okay, let us take a part, for example, any part of the beam. If you do a cut here, okay, your normal reaction will be, to oppose the 20 Newton, will be like this. It will be a negative reaction, okay, because n is counted positive when it will cause tension to the structure. So since when you put the convention for n, you will put it like this, but when you write sum of x, you will get n plus 20 equal to 0. So n is equal to minus 20. This will be the case here everywhere in your beam, because I have only, at any cut, I have only from the side AX. Okay? So if you want to represent n, it will be like this. So a horizontal force will affect the value of normal force, not of shear force. Okay. Now, sometimes it can affect the bending moment. In case, for example, I have it like this. Let's say you have an extension for the beam, for example, like this, and you are applying a normal force here. If you apply a force here, then it will affect the normal force, and it will affect also the bending moment, because it will be able to produce a moment. Okay, but if it is along the beam, it will not affect the shear, and it will not affect the bending moment. Okay,
Okay, thank you.
any other question on this? Okay, now we move to the bending moment diagram. For the bending moment diagram, you should look at the shear diagram, and you should look at your beam. Why you should look at your beam? Because look, sometimes the shear diagram will not be affected by couples. So if you have a couple on your beam, for example here, you cannot see it in the shear diagram. This is why, to draw the bending moment, you should look at both the shear diagram and the load acting on your structure. Okay, so you look at the load to see if you have any couple, because if you have a couple, you will have a jump in moment. If it is a clockwise couple, it is an upward jump or downward jump?
Upward.
Upward jump. And if it is a counterclockwise couple, it will be a downward jump. Okay, so now here we don't have any couple here, so no jump in moment. And at the beginning of the beam, we don't have a couple, we don't have a fixity, so we start from zero, okay? Because if I have a fixity, I will not start from zero, because if I have a fixity, then I will have a reaction moment here, and the reaction moment will cause a jump in moment. But as I have a pin or roller, so if you have a pin or roller and no couple acting at the point, then you will start your bending moment by zero, and also you should end by zero. So this is a verification also for you that I should start by zero and end by zero, because I don't have fixities and I don't have couples. And now, to be able to draw the variation of my bending moment, I will look at how my shear is valued. So first I start from zero. We know that M, okay, you have that V, the shear, is the derivative of M with respect to X. This means that V represents the slope of M. So if V is constant, then M is linear. Okay, if V is positive, then M is increasing. So here, as you can see, first V is positive here, so I will have increasing moment, and after 4 I will have a decreasing moment because V is negative. Now, between from this point to this one, I have V constant equal to 18. So what I can represent here, I can say that M is linear, and the slope, this is the symbol of slope. Slope is equal to 18. Now, to find the value of the bending moment at this point, I say that the variation of M is equal to the area under V curve. Okay? Because delta M is integral V dx. So the variation of M is equal to the area of this rectangle. So here all I have to do is to calculate this area. I say that this area is equal to 18 times this distance here is 2. Okay, so 18 times 2, so this is A1, is equal to 36. And since I'm starting from 0, so 0 plus 36 will give me a value of 36 for the moment at this point. Okay, then from here, from this point to this one, I have another area. I have a smaller value of V, it's 4, and the value of the distance here is 3 meters. So from here to here I have 3 meters. So the area will be A2. A2 is equal to 3 times 4 equal to 12. Okay, so what should I do here? V is constant, so M is linear. So here's the slope at this line is equal to 4. And the increase in bending moment is equal to 12. And since I was originally at a value of 36, then I do 36 plus 12. So I should end by 48 at this level. Okay, so 36 plus 12 equals to 48 here. Now, finally, after 5 meters, okay, I have the distance from here. So first here you have 2 meters, okay, and the value of shear here is minus 24. When I have a negative shear, so this means that my moment should be decreasing, and the decrease is equal to the area of this part between the shear and the x-axis. The area of this part A3 is equal to 24 times 2 equals to 48 meters. And since it was plus 48, I should go down 48, so I will get back to 0. And this is expected. I should verify that, so I should end by 0. So, and since here it's a constant shear, so the variation of V is linear, and the slope will be equal to the value of shear, which is minus 24. So the slope here is minus 24. And in this way, I have constructed my bending moment diagram. Okay? Any question on this? Okay. So let us do another problem.
دكتور سؤال ان احنا
Yeah.
اذا كان عندنا a moment بقلب الفيجر
Yes.
يعني not belonging to any force ساعتها
Yes.
نحن ما بنبلش at zero لما
بلا
بنرسم
بلا بنبلش at zero. بس مثلا let's say you have a moment here, for example, at the middle of your, let's say, of your beam. You have a bending a moment, a couple moment, a clockwise couple moment, let's say, of 20 Newton meter. So هلا أكيد your reactions will be different. يعني the reactions will be affected by the presence of the couple. Okay? بس البندنج مومنت at A حيكون زيرو والبندنج مومنت at D كمان حيكون زيرو. بس بالجراف شو بيصير؟ You will have here a positive jump. يعني هون مثلا you will have jump ترجع بتكمل على السلوب العادي. يعني كأنه just you did a jump here وأكيد رح ترجع تجي على زيرو. يعني the values will be different of course لأنه كل شيء حيتغير الرياكشن حيتغيروا. بس this is the profile of your graph in this case. Okay?
okay thank
Oh
you
yeah, we'll do problems with couples. Okay. Here we want to draw the shear and bending moment diagrams for the following beam. Sometimes they don't give us numbers, so we just represent function of the variables omega and alpha. Okay? First, the first step, as I told you, is to find the reactions. Okay? So here I have a fixity. Since I have a fixity, I should find what is the value. No AX because no X loading. So I have here AY and I have a couple. Okay? Now, the couple will be clockwise or counterclockwise, do you think? The couple should be in a way to have equilibrium, okay? But as you can see, your load is producing
Counterclockwise.
yes, yes, exactly, because your load is producing a clockwise couple, so the reaction at the fixity should be a counterclockwise couple, okay? Now, how to find the reaction here at the fixity? We do sum of moments equals 0, and to get the reaction AY, we do sum of forces equals 0. So let us start by finding AY. We have that sum of forces along Y equals to 0. So we have first AY minus, you have here triangular distributed load. So the force is equal to the area of the triangle, W times L over 2 over 2. So it's WL over 4. And also for the second triangle, it's the same dimension. So I can say times 2 equals to 0. So AY is equal to omega L over 2. Now, concerning the reaction AY, the bending moment AY M, the reaction moment at the fixity M. Okay, to get the reaction at fixity M, I will do sum of moments about. I can do about any point. I will choose A. Okay, so sum of moments about A equals to 0. Considering the counterclockwise as positive, I have plus M And now, for my distributed load to be able to get the moment, I can replace it by equivalent force. You know that when I have a triangular load, the equivalent force will act at 1/3 of the base. So this distance here is L over 6.
Doctor,
Now,
in the previous question, is there a reason we took the counterclockwise to be negative?
you mean when we did what? Sum of moments?
Yes.
In the previous question, we want to know, you have to determine you don't have couples, you want to determine the value of the reaction. You can take any direction as positive. But once you take the positive direction, you should respect it when you do the calculation. I don't know
Okay.
if, okay? Even here you can take, if you want, when you do sum of moment, you can say if you want to put the clockwise as positive, you can. Just you put it here instead of plus, what do you put? Minus m. Okay? So always in sum of moments equation, you are free to select the direction that you want, clockwise or counterclockwise. Just here, if you want, because I know that m is in the counterclockwise direction, I can consider the counterclockwise as positive and put plus m. But it's not wrong to take the clockwise, because the only difference will be here you put minus m. Okay? So if you work on the clockwise direction, it's minus m, and then the moment of the distributed load will be positive. You do plus the moment of this load and plus the moment of this load. So it's equivalent. You can select any positive direction. It's not a problem. Okay?
Yes, okay, thank you.
So here we replace the first distributed load, and we said that the value of it is omega L over 4. And it's acting at a distance of L over 6 here. Now, for this part also, I can replace it by a force at 1/3 of the base. So it's also equal to omega L over 4. And the distance from here to here, it's L over 6. Okay. So from A, it's L over 2 plus L over 6. Okay. So now we are ready to write the equation. So it is, if we selected the clockwise as positive, it is minus m plus omega L over 4 times L over 6, and plus omega L over 4 times L over 6 plus L over 2. Okay, L over 6 plus L over 2. So here you will express this is equal to 0. In this way, you will express your moment, reaction moment at A, function of omega and m. Okay? Once this step is done, now I am ready to start to draw my shear and bending moment time. So as you can see here, I have calculated the reaction and the moment reaction. Now we will start by the shear diagram. So for the shear diagram, as I told you, a couple will not affect it directly. It will just affect it indirectly through, it's a reaction. If you want, any reaction at the end will affect the final result. Because from the distributed load, if the distributed load will vary, the reactions will vary, okay? But a couple here will not affect the value of the graph of shear. It will not cause a jump, it will not cause anything. So when I look at the shear diagram, I just look at forces. So I have first at A an upward jump, so it's omega L over 2. I will start by plus omega L over 2, as you can see here. Now, since I have, let me zoom it a little bit so you can see both on the same graph. Okay. So here, first I start by V equal to omega L over 2. Then here, since my triangular load, I have a triangular distribution. Okay, so since V is linear, sorry, since omega, and here the variation of omega with x is linear. Okay, the variation of V will be second degree. Why? Because look, you know that omega is dv by dx. So omega represents the slope of V. Okay, so if omega constant, V is linear. If omega linear, V is second degree, etc. Okay, so always the degree of omega is the degree of V minus 1. Okay, so here, since omega is linear, then V is second degree. And since omega is negative, when omega is negative, because it's downward, okay, then V is decreasing. So here, the slope, as you can see, omega represents the slope of V. So I can say that I will start by a slope of a negative slope of omega. So here, phi is equal to the slope. I will start by a slope equal to minus omega. And then what will happen is my slope will decrease. Okay, so as my slope is decreasing, at L over 2, my slope will become 0. So as you can see here, this will give you an upward concavity because the slope is decreasing. So here, I will end up here at this point with a slope equal to 0. Okay, so the value of omega will give you the slope at each point. And since it's a downward force, so I can say that I am dealing with a decreasing shear. Okay, and then I have that my V is a second degree parabola because this is linear. So when omega is linear, V will be second degree. So this is the symbol of it, second degree parabola. Okay. Now, here what will happen suddenly? Suddenly I have change in shear. When I have, I have change in W. When I have suddenly change in W, this will mean I have sudden change in slope here. So W is again, it was 0, and suddenly it is a downward distributed load. So it's a negative slope for V. So then I will have a sudden change of slope at this point because it was 0. Then it will become negative again. It will become equal to minus omega again. Okay. Now, just before talking about this, how to know what is the value of shear at this point here? Delta V from this point to this one, okay, is equal to the area under omega curve. So here, delta V is equal to this area, and since it's a downward force, then it's a negative drop. Okay, so I have this area here is the area of a triangle. It's omega L over 4. So V should go down a value of omega L over 4. So I will say that delta V is equal to omega L over 4. If I consider that this is point, let's say this is V1, okay, then V2 at this point will be in a way that V2 minus V1. Delta V also, I should put a negative sign because it's dropping. So V2 minus V1, and V1 I can replace it by omega L over 2. V2 minus omega L over 2 is equal to minus omega L over 4. So this will give you that V2 is plus omega L over 4. Okay, so this is why here the value of V2 is omega L over 4. Okay, now as we said, after L over 2 we have a sudden change in slope. It was 0, then it is minus omega. So here phi is equal to minus omega, and then I will have the slope will be reduced, as you can see, because omega is becoming tending to 0. Okay, so the slope will be reduced until at the end of the beam we will reach a slope of 0. And of course here I will end up by 0. Why? Because the variation in shear is equal to the area under omega curve. You can see here that since omega is down, then I have a negative value of the area. Yani if you want, I will do minus the area, and the area is positive, but I will go minus a. So the area here is omega L over 4. Then I can say that delta V is minus omega L over 4. And since V at 2 was omega L over 4, then V at point 3 will be equal to omega L over 4 minus omega L over 4. It will give me 0. And this is expected to end here by 0. Who will tell me why? Why I can expect to end my shear by 0 here? Look, if you do a cut here and you want to calculate the shear, do you have any force here? And if you do a cut and you reject the other part, okay, you have the shear should be here up to be positive, to have the convention of positive shear. I don't have anything. I don't have a reaction. I don't have a concentrated force. So shear should be 0 here. Okay. This is not the case if I have a pin or roller. When I have a pin or roller, I have a reaction here. So of course the shear will not be 0. But since I don't have a reaction, I don't have a concentrated force, then at the end of my beam here, I will have a shear of 0. Okay. Any question on the shear diagram? Okay. So now we will pass to the bending moment diagram. And here I should pay attention that I have at the beginning of my beam, since I have a fixity, I have a counterclockwise moment. A counterclockwise moment will cause for me a negative jump. This is why I will start my curve by a negative value, which is minus 5 omega L square over 24. Okay? Now, in order to continue, I should look at V. V is the slope of L. So to start with, my V is positive everywhere. This means that my bending moment is increasing. Now, I will start first by a slope of omega L over 2, which is positive. So here, my slope was omega L over 2. Then my slope will be reduced gradually to reach omega L over 4 at this point. So at this point, my slope is omega L over 4. And finally, at L, my slope is 0. So as you can see, the slope is decreasing. So I have here a downward concavity. I can also expect that I will have downward concavity. Why? Because from the course material, the second derivative of m with respect to x is w. Okay? And since w is negative everywhere on my beam, يعني, here if you want, نحن بالكورس ماتيريال حطينا second derivative equal w معتبرين انه w positive up. Okay? But here you have that w is downward. So if you want, here second derivative is because w is taking the absolute value, it's minus w here. Okay, so we can say that it's a negative second derivative. this means that the concavity is downward. So it's a sad face. When you have second derivative positive, then you have a smiley face, concavity is upward. Okay. When you have second derivative negative, then it is a sad face and concavity is down. Okay. So the slope here was omega L over 2. The slope here is omega L over 4. So this is the slope.